Welcome to the deep dive. Today we're looking at a stack of sources detailing, well, a pretty fundamental shift driven by physics, moving from classical computation over to quantum computing.
Right. And the core story isn't just faster computers.
Yeah.
It's about acknowledging that classical hardware, the engine for the last 50 years, it's starting to hit some real physical limits.
You mean things like Moore's law slowing down?
Exactly. Moore's law is slowing. Transistors are getting so small we're struggling with heat, with energy consumption. It's becoming astronomical.
So quantum computing steps in here.
It emerges as a necessary complement, really. Not something to replace your phone or laptop, but a specialized tool. It's for tackling the kinds of complex problems classical machines just choke on.
Like what specifically?
Things like large-scale simulation, intense optimization problems, and maybe most urgently, securing our global data infrastructure.
Okay. So our mission today is to really unpack that difference. What makes a quantum computer tick, fundamentally?
Yeah, dissect the power of the qubit.
And then explore where it actually makes a difference in the real world. We've got sources talking medicine, finance, even climate science.
Definitely. And we need to zero in on two really critical interconnected battles. First, the race to create quantum-resistant cryptography.
Ah, the PQC stuff, post-quantum cryptography.
Right. And second, something often overlooked, the potential energy efficiency. Quantum systems might actually offer a surprising advantage there.
An energy advantage. Interesting. Okay, let's start at the beginning then. The absolute foundation, bits versus qubits.
Perfect place to start.
So everything we use now, right? Your laptop, the cloud, the internet, it's all built on classical bits, simple binary units.
0 or 1, on or off, stable, predictable, processed sequentially using Boolean logic we've had for decades.
Straightforward. Now, the quantum revolution starts with the qubit. How is it different?
The key difference is superposition. Think of a coin spinning in the air before it lands. It's kind of both heads and tails.
Okay.
A qubit can be 0, it can be 1, but crucially, during computation, it can exist as both 0 and 1 simultaneously.
Both at the same time. How does that help?
It allows the quantum system to explore many possible solutions or paths at the same time. It's like having built-in massive parallel computing.
Right, so it explores possibilities concurrently instead of one after another.
Exactly. And that power gets amplified by the second really weird quantum property, entanglement.
Ah, yes, Einstein's spooky action at a distance.
That's the one. Entanglement links two or more qubits. Their fates become intertwined, their states instantly correlated no matter how far apart they are.
So changing one instantly affects the other, even across a room or further?
Or further, yeah. Theoretically, across the universe. This linkage allows for incredibly fast and precise coordination within the calculation.
And the result of superposition and entanglement together is exponential power.
That's the crucial takeaway. Classical computing power tends to scale linearly. Add more processors, get proportionally more power. Quantum power, it explodes exponentially.
The numbers are pretty staggering. One source mentioned a 50-qubit machine could evaluate over a quadrillion states simultaneously.
It's an almost unimaginable computational space, far, far beyond what even the biggest classical supercomputer clusters can handle today.
Ah, there's always a but, isn't there? This power comes at a cost.
A huge cost. Fragility. Qubits are incredibly sensitive. Any tiny disturbance from the environment, a bit of heat, noise, even a vibration can destroy the quantum state.
That's decoherence, right?
Exactly. Decoherence. It's the arch nemesis of quantum computing. To fight it, these systems need extreme isolation.
Which means those pictures we see of huge, complex refrigerator.
Precisely. Dilution refrigerators often cooling the quantum chip down to millikelvin temperatures, just fractions of a degree above absolute zero.
So we've traded the heat problem of classical chips for this deep-frozen, high-maintenance genius.
You can put it that way. It's powerful, incredibly so, but also incredibly delicate and expensive to run just from the cooling perspective.
Which brings us to the practical question. Where is this fragile power actually worth the trouble? Which problems demand it?
That's the key. We need to look at sectors where classical machines are already hitting a wall. Science and health are prime examples.
Why there?
Simulation, especially a molecular simulation. Classical computers really struggle to accurately model how molecules interact at the quantum level. The complexity just scales too quickly for them.
But a quantum computer is a quantum system.
Exactly. It's like using a quantum system to study another quantum system. It's a natural fit. This could revolutionize drug discovery, for instance.
How so?
By letting researchers accurately simulate how a potential drug molecule interacts with proteins in the body. or understanding things like protein, folding a notoriously hard problem in biology with huge implications for diseases like Alzheimer's.
And beyond medicine, materials science.
Absolutely. Designing new materials with specific properties, maybe for better batteries, more efficient solar cells, lighter aerospace components. Simulating the quantum interactions lets you design them from the ground up.
Okay, that makes sense for science. What about finance? Optimization seems like another area mentioned.
Definitely. Quantum computers excel at what's called combinatorial optimization, problems with tons of variables all interacting at once.
Like portfolio optimization, finding the best mix of assets.
Precisely. Or improving financial modeling, assessing risk by simulating countless market scenarios simultaneously. Classical methods often have to rely on approximations for these kinds of things.
And this optimization power extends beyond finance too, right? Logistics.
Yes, big time. Optimizing complex supply chains, for example. Figuring out the most efficient routes, managing inventory dynamically based on real-time changes. Sources mentioned Volkswagen exploring QC for traffic flow optimization in smart cities, too.
Managing complexity, that seems to be the theme.
It is, and it applies to even larger systems. Think about weather forecasting or climate modeling.
Those are incredibly complex systems.
Right. Analyzing all the atmospheric interactions is a massive computational task. Quantum computers hold the promise of doing that much more effectively, leading to more accurate forecasts and better climate models.
Any other big systems?
Power grids. Optimizing national or regional power grids, especially with the rise of renewables like wind and solar, which are inherently fluctuating. QC could help balance load and integrate these sources much more efficiently.
Okay, before we dive into the security arms race, you mentioned quantum key distribution, QKD, as a defensive measure.
Right. QKD is about secure communication. It uses the principles of quantum mechanics to allow two parties to generate a secret key.
And the quantum part makes it secure.
Yes, because if anyone tries to eavesdrop on the quantum channel while the key is being exchanged, the very act of measuring the quantum state disturbs it. This disturbance is immediately detectable by the legitimate users.
So you know if someone's listening in.
Instantly. It offers theoretically unbreakable key exchange. The source has highlighted China's QUSS satellite mission as a major proof of concept.
How far did they send a key?
They successfully demonstrated QKD between the satellite and ground stations over 1,200 kilometers apart. It showed long-distance, highly secure communication is viable.
Okay, so QKD is the shield. Now let's talk about the sword. The threat quantum computers pose to our current security.
This is where the real urgency comes in. Algorithms like Shor's algorithm, which could run on a sufficiently powerful future quantum computer, are specifically designed to break the math underlying most current public key cryptography.
Things like RSA and ECC, the stuff protecting banking, emails, secure websites.
Exactly. All of that relies on problems like factoring large numbers or calculating discrete logarithms, which are incredibly hard for classical computers, but potentially easy for a quantum computer running Shor's.
So we need new cryptography that even quantum computers can't break. That's post-quantum cryptography, PQC.
Right. And organizations like NIST, the U.S. National Institute of Standards and Technology, are in the final stages of standardizing the first waves of PQC algorithms.
The sources mentioned candidates like dilithium, Falcon, and Rainbow. What are the trade-offs? It's not just about being quantum-proof, is it?
No, it's a complex balancing act. You need security, of course, but also efficiency. How big are the keys? How fast is the encryption and decryption? How much data does it add?
And how do the candidates stack up?
Well, many of the leading ones, like dilithium and Falcon, are lattice-based. They rely on the difficulty of certain problems in complex mathematical lattices. Falcon 512 stands out in the sources for offering strong security with relatively small key and signature sizes.
Why does size matter so much?
It matters hugely for real-world applications, especially over networks. Think about secure web connections using TLS 1.3. There's a limit to how much data you can shove into the initial handshake messages, particularly the digital certificates.
So if the PQC algorithm creates huge keys or signatures,
It might not actually work with existing internet infrastructure.
Yeah.
And this is a real problem highlighted for Rainbow, which is a multivariate-based candidate.
Rainbow is secure against quantum computers.
Theoretically, yes, but its certificate sizes are often too large. They can exceed the standard limits for X.509 certificates used in TLS. So the connection just fails before it even starts.
So a theoretically secure algorithm is useless if it breaks the internet?
Pretty much. Falcon 512, with its much smaller certificate size, is way better suited for these network-constrained environments. Then there's speed health. Dilithium-2 seems fastest for signing small messages, but maybe some rainbow versions are faster for verifying large ones, if you can establish the connection. It's messy.
It sounds like a classic engineering trade-off. Theoretical perfection versus practical reality.
Absolutely. Network constraints are a huge reality check for PQC.
Okay, this is fascinating. Now, let's pivot to that energy surprise you mentioned earlier. This feels like it flips the whole narrative.
It really does. Because we started by talking about classical computing hitting energy walls, right?
Right.
And quantum computers needing massive energy just for cooling.
Yeah, the dilution refrigerator.
But the actual computation, the quantum operations themselves, turn out to be potentially incredibly energy efficient. It's been rigorously proven, theoretically at least for certain problems like Simon's problem, that quantum computation offers an exponential energy advantage over classical.
Wait, exponential advantage, meaning it uses exponentially less energy.
For the right kinds of problems, yes. Once the system is cooled down, the energy needed to flip qubits and perform gate operations is minuscule compared to powering billions of transistors in a classical supercomputer doing the same complex task.
That's huge. What kind of reduction are we talking?
The sources suggest maybe a 256 qubit machine could cut total power for specific suitable tasks by something like 99.9% compared to a high-performance classical system.
99.9%, that completely changes the calculus. It's not just about speed, it could be about sustainability.
Exactly. It positions quantum computing not just as a performance booster, but potentially as a key technology for tackling energy-intensive scientific computing in a more sustainable way. It's a really compelling, counterintuitive point.
Okay, let's shift gears slightly to the hardware itself. We hear names like IBM, Google, D-Wave. Are they all building the same kind of quantum computer?
No, not at all. There are fundamentally different approaches. The most common one, pursued by IBM, Google, Rigetti, and others, is the gate-based model.
Gate-based, like logic gates in classical computers.
Sort of analogous, yes. The idea is to build a universal quantum computer that can run any quantum algorithm by applying sequences of fundamental quantum gates, often called the Clifford plus T gate set.
So, a general-purpose quantum machine.
That's the goal. But because qubits are so fragile, this approach relies heavily on developing complex quantum error correction codes, like surface codes, to protect the computation from noise and decoherence. It's a huge challenge.
And then there's D-Wave. They often claim very high qubit counts, thousands sometimes, but they seem different.
They are fundamentally different. D-Wave uses quantum annealing. It's not a universal gate-based computer.
What is it then?
It's a specialized machine designed only for solving optimization problems, specifically a type called QUBOs, quadratic unconstrained binary optimization problems.
How does annealing work?
It maps the optimization problem onto an energy landscape, like a hilly terrain. The quantum system then naturally settles into the lowest energy state in that landscape, which corresponds to the optimal solution of the problem. It finds the bottom of the valley, metaphorically speaking.
So it's a specialized solver, not a general calculator.
Exactly. It's useful for certain optimization tasks, but you can't run Shor's algorithm on it, for example. It's also worth noting there's been some controversy.
Ooh.
Yeah, some research has suggested that for certain problems, D-Wave targets highly optimized classical algorithms running on regular computers can sometimes find solutions just as fast or faster.
Yeah.
So the extent of its quantum advantage is sometimes debated, but for specific QUBO problems, it remains a distinct approach.
So gate-based for general purpose, annealing for specific optimization, different tools for different jobs.
That's a good way to think about it. And it leads to the bigger picture takeaway from all this.
Which is?
The future isn't purely classical or purely quantum. It's going to be hybrid.
Combining the strengths of both.
Exactly. We'll continue using robust, reliable classical computers for everyday tasks, general purpose computing, storing data. But for those specific, incredibly hard problems, drug discovery, materials science, complex optimization, perhaps breaking codes or securing communications, will increasingly turn to specialized quantum processors, likely accessed via the cloud initially.
That makes a lot of sense. Classical for breadth, quantum for depth, and maybe, surprisingly, for energy efficiency on those deep problems.
Precisely, leveraging the best of both worlds.
Well, this has been incredibly insightful. Thanks for breaking down these complex sources and navigating us through bits, qubits, security, and even energy.
My pleasure. It's a fascinating field, constantly evolving.
And for you, the listener, we always like to leave you with something to chew on. A final thought. Given that proven theoretical exponential energy advantage for quantum computation on certain problems, forget speed for a moment. What huge energy-guzzling problem currently run on classical supercomputers might be one of the first to be shifted to a quantum solution purely for sustainability and energy savings, even if it's not necessarily faster initially?
Hmm. Interesting angle.
Think about something like global climate modeling, which consumes megawatts of power today, or maybe optimizing the entire energy grid itself. Could the green advantage actually drive the first killer app for quantum rather than raw speed? Something to mull over until our next deep dive.